So it is my distinct pleasure to be here. I'd like to thank the organizers for invitation, also for the kind introduction. So this audience is no doubt heard by now multiple times about this idea or something which is going on, which is sometimes called quantum revolution. So in fact, it's very hard now to avoid hearing about it. So almost daily in the news, we see some new development. Over last year, 3 companies whose core business is quantum computing went public. People are thinking about building the entire quantum cities. So what is it about? It is about the fact that information, its acquisition, storage, transmission, and processing is fundamentally rooted in physics. And the progress in technology indicated already a few years ago that ultimate elements of sensors, processors, and transmitters will eventually become of quantum size. So this audience probably does not need a reminder that, for several decades, technology have been driven by the Moore's law, and people recognized already maybe a couple decades ago that there will be a time when the size of the transistor will become comparable to the scale of a single atom. Now, you all know that people are very creative, and so whereas now we would be nominally at the end of this Moore's law, I mean, there has been a lot of developments, basically figuring the ways to still kind of scale and improve the performance of the classical processors. Nevertheless, we are, closing this gap where basically we can no longer consider a transistor as a classical device, as a classical system. And this is what people started thinking about already almost 40 years ago. And then they realized that in principle, single atoms or single elementary particles could in principle be used as memory and quantum processors. So indeed, the single atoms, electrons, nuclei, and photons can acquire, carry, store, and process quantum information. So why is this special? So the reason is that at the level of these fundamental particles in the microscopic world, the physics of systems and devices is governed by something which is called quantum mechanics. This quantum world is actually very strange and very weird in many ways. So, for example, quantum particles can be in multiple different states or different places at once. So that's the idea of the quantum superposition, as indicated on the left plot here. This is not something that we are, used to in a common everyday life. Nevertheless, through almost 100 years of experimentations, we actually know for sure that the particles at a microscopic level can have these weird properties. Moreover, if this superposition state is delocalized in space, it leads to something which is called quantum entanglement, quantum correlations, which can show up at a distance between when particles, for example, are here in Boston and in Bremen at the same time. So this quantum entanglement is something which really perplexed even the founding fathers of quantum mechanics. Nevertheless, we by now know that it's a real physical phenomenon. So to get you kind of an illustration why this actually quantum frontier is exciting scientifically, I would like to point out that there is more than 100 years worth of Nobel Prizes given in the field. So starting from Einstein and Bohr in 1922 to 2022, the Nobel Prizes of this year given by Alana Speer, Anton Zeilinger, and John Clauser. Now, how is this superposition and entanglement? How are these properties are relevant to what we are talking today, to computers and information processing? So quantum computer is actually a device which can potentially harness this idea of superposition to process information in a fundamentally different way. And it's fundamentally different from every computer which has existed up to date. And so in the quantum computer, bits of information are replaced by quantum bits, which exploits this effect, superposition and entanglement. And when used correctly, the emergent phenomena, which is called quantum parallelism, can solve some problems exponentially faster than a classical computer ever could. The central element I'd like to emphasize again is the idea of replacing a bit of information, the 0 and 1, which store the information in every classical electronic gadget, by this idea of the quantum bit, which can be in a superposition of both 0 and 1 at once. And this is very special. This is what gives quantum computers their power. So to indicate the power of quantum superposition, I would like to consider just one example. Consider individually controlled single atoms in which you encode these quantum bits, this superposition, so 0 and 1. So it turns out, and this, is a conceptually simple device, but also, as you will see in a minute, quite realistic. So it turns out that these individually controlled atoms can store quantum bits of information. But then if you start increasing the size of this register, you very quickly come to the point which is actually really quite astonishing. And in fact, if you just have 300 atoms to store 300 qubits, so using this idea of quantum superposition, it is possible to, in principle, simultaneously store and evaluate more solutions than the number of particles in the entire universe. So that's the basis, and that's the motivation to study and build quantum computers. The question is, how can quantum computers change our world and affect everyday lives? The answer to this question, I should say right away, is currently unknown, because this is new and emerging technology. But one can divide all problems which quantum computers can potentially tackle into two different categories. Some are difficult problems that are currently solved by conventional computers, but they are solved in a kind of using expensive brute force methods, which are fundamentally inefficient. And another class is what I would call impossible problems, problems which are really not possible to solve, any existing technology. Admittedly, this is not the problems that, the computation that, is something that, you have to do kind of every time you log on your internet account or use your cell phone. But there are many of these problems around the world which, potentially have a great impact for both, science, technology, and society. So here are some examples. Understanding and designing complex quantum materials. This problem is fundamentally quantum mechanical. Solving it classically is very expensive, very inefficient. Understanding chemical structure and controlling chemical reaction is also fundamentally quantum mechanical problem, which is actually very hard to solve classically. Optimizing solutions for networks, logistics, finance is another example of the very hard problem, which kind of borders between this, kind of hard and impossible. But then there are these impossible problems, which something like factoring, sampling, accelerating artificial intelligence. And, to be honest, in truth, we really do not know now what other problems exist, which are very hard, or impossible to solve currently, which quantum computers can potentially solve. So to address these problems, there are different approaches which are currently being explored. Some involve something which is called programmable quantum simulators. So these are machines which you can program, and you can basically kind of run, quantum evolution. And the other kind is something called universal quantum computers. I will give some examples of both of these in the following. So I would like to turn now to the question of building quantum machines. And this is a quote from one of the pioneers in the field, Richard Feynman, who about 40 years ago started musing about ideas of ever building, something like a, programmable quantum simulator or quantum computer. And he thought about replacing, the single transistor, which at the time had about 10 to the 11th atom, by a single atom. And he said, oh, such a nonsense is very entertaining to professors like me, and I hope you will find it interesting and entertaining also. Fast forward 40 years, there are now a wide variety of platforms which are being explored. People using charged ions, neutral atoms, superconducting qubits, photons, defects, and solids. And the frontier of the field now is addressing something which is sometimes called, ultimate quantum rivalry. So this can be understood in different ways. You can think about this as a competition between different platforms, or sometimes even between different countries. But actually, it's much more fundamental. So it's competition between two forces of nature. One is a force of controllability, and another one is a force of scalability. Controllability means that you basically have to really change, and control atoms one at a time while preserving their quantum mechanical properties. And scalability, you need many, many of those atoms or qubits if you want. So these kind of forces are at play. This competition between these two forces are at play in many areas of human activities. So, for example, if you have an organization which has, a number of, smart, people like a PhD physicist, and there are many of them, it's by definition becomes difficult to control. But in this quantum mechanics, what we are at against this frontier is exactly this competition between these two forces. So the kind of state of the art and the current frontier is something which I will sometimes call the era of quantum discovery, in which we can use machines to perform, quantum machines to perform tasks that classical computers can just not perform. And that typically involves controlling over 100 qubit systems. And we use these machines to both implement and test some useful algorithms and explore new applications. And we also use these machines to figure out ways how to build bigger and better quantum machines. I'd like to now focus on one specific approach towards building quantum machines, and this is something that my lab at Harvard and also Quera Computing is pursuing. And it's actually the approach in some way which also have been pioneered by Richard Feynman. So kind of early on, he started thinking about, in principle, making and computing devices in which the numbers are represented by the row of atoms, with each atom in either of two states, 0 and 1. And then you turn on quantum evolution, and ones move around, zeros move around, and finally a certain bunch of atoms is being measured. So he thought at the time nothing could be more elegant. Fast forward 40 years ago, these are the kinds of devices which we actually now can implement and experiment with in our lab. In particular, about 5 years ago, we built a device for the first time. It was kind of the largest system in which we could control over 50 single atoms. So what you see here are the images of individual atoms, so which basically are positioned at will in a vacuum cell using beams of lights, using something which is called optical tweezers. And then we encode quantum information in the states, in internal states of these atoms, and then we can actually control it by just shining laser beams to switch these zeros and ones, much like the kind of the original idea or dream of Feynman. In particular, what we do is we do quantum logic by switching atomic states into the so-called Rydberg states, where the atoms can talk to each other, they can interact with each other, and this way we can really execute, quantum logic operations. The state of the art right now is control over about 200 atomic individual atomic qubits. So here are the kinds of lattice geometries which one can produce. So these are literally kind of artificial two-dimensional materials, where you can basically write, you have essentially a canvas in which you can draw, you can, write, you can position the atoms at will. And in fact, you don't need to create an ordered material. What you can do, you can, for example, program the atom array that you can desire, and then press a button, and here comes the pattern what you want. So what you see here are all pictures of individual atoms, single atoms which can store qubits. And then what we do by shining lasers of them, we can actually make connections. We can basically, draw the logic operations, the logic circuits, and basically that way perform quantum computation. So this is the system which actually have been realized in our Harvard lab slightly over 2 years ago, and those last 2 years have been actually quite special, I would say. And that we could really kind of play with the system to explore a wide variety of different scientific avenues. We explored different exotic states of matter, exotic phases of matter. We pushed the system far away from equilibrium and watched how it evolves, how, for example, the entanglement is created in the system. So I will talk a little bit today about realizing topological spin liquid. This is a state of matter which have been predicted over 50 years ago and have not been seen in a lab until last year. And I'll talk also a little bit about, kind of more practical things like accelerating combinatorial optimization, and also thinking about the future, building kind of universal error-corrected quantum machine. So one big development of the past month have been that in our startup company here in this building, the first quantum machine has been built such that it actually can be hooked to the cloud. And in fact, it became publicly available on November 1st. So I'll give you now a little bit of the kind of, insight into all of these exciting directions. So the first is the idea of a kind of understanding and designing new quantum materials. And here, the example is something which is called topological quantum material. So topological quantum matter is the idea which has been postulated by Phil Anderson, a famous condensed matter physicist who was at Bell Lab at the time. And he basically postulated that there might exist some special states of matter where basically the properties of the system is governed by the system's topology. So the topology, as hopefully many of you know, is a branch of mathematics which kind of allows one to classify objects by their shapes. So for example, from the point of view of topology, a coffee cup and a donut is a single thing. And while initially this idea was considered kind of very exotic, very, hypothetical, over the last, 40 or so years, these topological materials became really a mainstream of material science research. And the idea is these topological materials have some intrinsic robustness. So you really need to cut this, donut to convert it, for example, to a donut hole. You cannot continuously deform it. Moreover, about 20 years ago, people realized that these ideas of topology can be used to design potentially robust quantum bits and build, fault-tolerant quantum computers. And in fact, the topological quantum computing is the basis for the entire research program of the Microsoft quantum team. Despite all of these remarkable developments, up to now, up until last year, there was no single experiment in a condensed matter system and a real material system which provided an experimental evidence for existence of such topological matter. And as actually the situation has changed about a year ago, we used this programmable quantum simulator, involving 219 qubits to actually build this kind of state, which actually is quite exotic. So it is a superposition of the state where, basically atoms are arranged in a very different ways, So basically, if you look at these plots, you don't see an obvious order. So this order really is encompassed in systems topology. It was really quite exciting time in this field. So this picture is, I believe, is a Scientific American cover from, maybe a decade or so ago. I'm sure that the artist who drew this, thought that physicists, became completely crazy. They're trying to do this kind of knots and, but things like this can now be really kind of realized and tested in the lab, and they give unprecedented insights into topological matter. So the programmable quantum simulator emerges as a real special tool, which is complementary to and in some way more powerful and both analytical and classical numerical simulations. And there are many kind of exciting potential applications, ranging from simulating lattice gauge theory to insights into developing new practical topological materials and also exploring this idea of topological quantum computing. The second example I would like to give involves this application of these programmable quantum machines to optimization. So combinatorial optimization problems are very important for many different areas of technology. One specific example of this kind of network optimization involves a problem called maximum independent set. So what you see here is a graph, where the problem is to basically color as many nodes in this graph as possible, but the statement of the problem is you should not be able to color the nodes which are connected by the link. So this problem is called maximum independent set. So it's an example of an P-hard problem. And it has many practical applications in logistics, networking, finance, and things like this. So the big development of this year is that we were able to actually very efficiently encode this problem into this atom array platform, and actually through the closed loop optimization procedure, explore if we can use the quantum machine as a kind of accelerator to the conventional classical methods. And in fact, in this work, we for the first time observed evidence for the superlinear speed up for the kind of real world kind of practical problem. So here are some, for those of you interested, here are some details. So we focused on something which is called unit disk graph, where basically nodes are connected which are within certain separation distance between each other. And then using atom array platform, we were able to explore basically graphs, using systems from about 70 to almost 300 qubits. And what we found, for example, is that even for the similar size of the graph, sometimes the problem hardness, really differs by orders of magnitude. And focusing on, in particular, hardest instances, we were able to see a speed up when we go in the regime of the so-called deep circuit. So basically, we need to evolve quantum system for long enough time that the quantum system can basically explore the entire graph. So doing that really kind of required reaching kind of the product of number of qubits towards surface depth, which are actually kind of couple of orders of magnitude larger than those which are accessible with different platforms. And it really kind of indicates, you know, the power of this programmable quantum simulator approach. And, you know, also a potential for using the system to solve this kind of real world problems. So the big challenge here is now to scale up, to go to larger systems, you know, involving hopefully, you know, thousands of atoms, but also kind of, you know, improving the quantumness of the system, reducing the errors. And this is something that, you know, brings me to this last example, where, you know, problems like factoring, you know, require, you know, large systems involving thousands of qubits and also very deep circuits, so that you can actually implement many gates. And the key challenge there is fighting with errors. So one other big development from this last year has been a realization of a new architecture, which actually allows you to very efficiently accomplish this goal. In this architecture, what we do is we use our atom array as a kind of a living organism. So in the sense that the connectivity and the position of the qubits changes as the quantum evolution proceeds. This is very special because in all existing quantum or classical hardware platforms, basically the connectivity is fixed at the point where you design your chip, where you actually introduce these connections. And, you know, after that, there is nothing you can do. This is different in our approach. What we can do, we can, you know, create an atom array, you know, execute some logic operations, then reconfigure this array without losing quantum information, and then proceed in this way. So as an example, what I'd like to illustrate here is realization of something what's called topological quantum error correcting code. So it's actually related to the spin liquid example, which I mentioned. But, you know, kind of, you know, what is it? What is quantum error correction? So basically, in the quantum error correction, what you do, you use redundant encoding. You use several physical qubits to encode a single logical qubit. And basically, what you want to do, you want to use this logical qubits as a building block of fault-tolerant quantum computer. And the way how you correct the errors, you measure something which is called stabilizer. You do basically collective measurements on this grid of the physical qubit to basically find out if the error occurred, and if that occurred, to correct it. So, but, you know, and it's connected to this idea of topology. So if you have something, for example, on a torus here, you know, this is, you know, basically this qubit in this case is protected by this topology of the torus. But you'd say, well, wait a second. So you have two-dimensional system, you know, how can you implement this kind of, you know, toric code which lives on a torus? That seems hard. Well, it turns out it is possible to do it, and the approach is actually kind of reminiscent to something which, you know, 20 years ago everyone knew about. At the time, there was magnetic hard drives, and there was a, you know, kind of essentially a magnetic, you know, head which you sort of, you know, you could use to kind of move around your system to read out the information. So in fact, what we implemented this kind of, you know, magnetic, you know, head, but instead of a classical readout element, what we did is we actually stored qubits in this head, and by moving them around, we were able to actually perform this error correction. So in fact, in our case, 8 qubits have been part of this head, and what you see is that they are moved around, and basically kind of, each red circle is the quantum gate, quantum logic operation, and then they're moved across all the system to complete this torus, and then we kind of move them into readout zone. So we're actually very excited about that, because it really opens a path towards really trying to implement algorithms with logical qubits, with kind of built-in fault tolerance, potentially at large scale, and kind of really start using this kind of algorithmic qubits for the applications. So I maybe have 2 more minutes, and I cannot leave the stage without mentioning another very exciting development. So Quera Computing, a startup company which was started out of our labs at Harvard and MIT in 2018, has by now almost 50 employees. And the mission of Quera Computing is to accelerate application development, also interfacing with potential customers via 2 approaches. One is by partnering and basically working on core design of algorithms of the type, for example, I showed for the maximum independent set. But another one is by basically providing a broad access, easy access to these quantum computing devices. And, this is actually has been sort of the development of November. In fact, on November 1st, Aquila, the Quera's first generation machine, became available on a bracket AWS cloud. So it was a little bit of hello world moment. So what you see here are pictures of actual central element of the Quera machine, as well as this graphs which one could create. So it's very similar to these graphs which you have seen before. So this machine is relatively easy to program. So in fact, you can describe systems geometry, you can define the pulses, kind of, how you excite, how you make the connectivity and make the atoms interact. And then basically, you can run your algorithm and analyze your results. And it's actually aided by the software kind of interface blockade, which has been developed here. It's actually, interestingly, it's a little bit too advanced to integrate right away with the AWS circuit, but maybe this will change, in future. So the big development, this is the first, 100, plus qubit machine, which really operates in this kind of new regime of quantum discovery. You can really run these machines to actually discover new things, in a way, I think about it as a kind of a small linear hadron collider, and it's kind of an amazing feat that, that the experiment, which has been, done just 2 years ago and published in Nature, has been now sort of brought to the customers, to the general access. And we are growing. We are looking for new team members, looking for new partners, customers and collaborators. So I think I'm closing here, and I hope I convinced you that quantum science and engineering is exciting interdisciplinary field. We are entering this era of quantum discovery, where we can use quantum machines for scientific applications, and also on the cusp of what's called quantum industry, where new revolutionary potential applications and perhaps even products can be foreseen. So with that, I would like to thank you for your attention. And when we're not working, we also have some games to play. Thank you.
Thank you. We're going to open it up for some. I assume that applause was for him and not me.
Mm-hmm.
A little hurtful. We're going to open it up for questions. I did want to start you off. We have the team in Bremen who are going to ask the audience. We have an online chat with people monitoring those questions. First question that came in for you. How soon do you think quantum computers become our new today, the new norm?
So that's a very good question. So I personally don't think that quantum computers will replace classical computers. So the best way to think about them as a kind of accelerators. And in some way, in the world of science, they are already kind of a norm. So as I already mentioned, we actually have, even in our lab, we made some, discoveries. We found things which, have not been predicted. And, this has really stimulated new fields of research. I like to think about, quantum computer development as a kind of almost in some way parallel to classical computer development. So the first applications of classical computers were purely scientific, and, people could not predict that every one of us will be carrying, a computer in our pocket. So, and we are definitely, like at the point with quantum computers where they are already useful for science. If, when, and how they'll make and transition into our everyday life gadgets, I would say that remains to be seen. This is really unclear.
Fantastic. Thank you. I'm going to open it up to our friends in Bremen. Do you have any questions from the audience?
Thank you. We don't have any questions. Unfortunately, we don't have the time. We're gonna jump right into our next speaker. But thank you so much, Boston. Thank you, Kyle. Thank you, Mikhail. Have a lovely day.